Hello, my name is H.S. and I'm in Mr. Overton's... Oh, I'm not going to do that. Okay. 8th hour class, and at this moment I'm going to test to see if the 2-second rule during driving is actually valid or not. Okay, so I'm going to first have to explain to you guys what the 2-second rule is, just in case you guys don't really know, so you never know, but it's always safe. Okay, so I pretty much got some of the cars from my childhood that I sometimes use. They're very helpful, actually. So we're gonna use 2 of them, or maybe more, to so that I can show you exactly what I mean about the 2-second rule. So with me, I know you guys hate shaky cam. It gets me dizzy too, but hang on, just bear with me. I'm going to build us a road so that I can demonstrate what exactly the 2-second rule is. This may take some time, but lucky for you, I'm going to fast forward through it. Hello, welcome to, let's call it, Adobe Road. Let's just call it Adobe Road, just so it's more formal. I got a little sign for it. There, Adobe Road. So let's say Adobe. Anyway, focus on the project, because you're forced to watch this, and you just chose it. We're going to use this, I'm going to use this as the test track for me demonstrating. So, just going to pick 2 cars and pretty much walk through exactly what the 2-second rule is, in case you don't know. And okay, basically here's the 2-second rule. What the 2-second rule is about. Okay. 2-second rule is referring to the amount of space between you and the vehicle in front of you. What this means is that there should be at least 2 seconds time count when you or the driver in front of you passes a sign. For example, I'm about to place this paper crane as an example, as a sign. So you count for 2 seconds as soon as the car A, which we'll call that produce car, pass the sign. That's 1, 2. There you go. Thank you, Eddie. Okay, so during those 2-second counts, if you can't count to 2 seconds as soon as before you pass through that sign, that means that you're too close or too far away. So that. Okay. Before we do any of that math stuff, I'm just going to point out 4 main checkpoints that I used during the solving it. So, important checkpoint number 1 is before car A hits the brakes. Not stops, but before car A hits the brakes. There we're just gonna reveal the velocity of both cars and the distance that is between them. Checkpoint 2 is the reaction time. During that, I'm gonna check the distance that car A is going to travel during the reaction time, and the distance of car B is going to be during the reaction time after car A puts its brakes on. And 3, car A stops. This is when car A is just stopped. We're going to figure out the distance between both the cars after car A is done moving, and the current velocity of when car B, its current velocity. Now, step 4 is when hopefully car B stops, and that's what we're hoping for. Okay, so let's start. First, we know that both cars are going to be starting at around 50 miles per hour. I say it out loud so you guys can actually be able to understand what I'm writing. So let's convert it to meters, because that's what all the scientists do, right? Right. Anyway, so everyone knows that there are about 5,280 feet in a mile. So we got that in our hands. So I'll just write that there, times 280. Now with my advanced multiplying skills, I'm just gonna do this quick for you guys. Should do this early. No, well, this is all in my head, but I'm just not stalling. This is not stalling at all. So we know that when you multiply that together, you're gonna get 264,000 feet. Why did I convert to feet? Because I know everyone knows the conversion of feet to meters, which is that's meters. Okay. 33. No, it's not. 3.3 feet per meter. Everyone knows that. So with this number, we're going to multiply that. We'll divide that by 3.3 feet, because 3.3 feet equals 1 meter. Yeah, everyone knows that. So with my advanced dividing skills, I have those two. We are going to divide that by 3.3 to get the magic number. Oh my gosh, you can't read that. I'm sorry if you have to read this, because I swear. Okay. So once again, I'm good at dividing by my head. Let me just think. So with my mind, I got 1, 2, 3, 4, 5. So 80,000 feet. I mean meters. So what? Yes. 80,000 meters. Very important. As I was saying, let's convert the meters into, well, they're already converted, but that's meters per hour. Now that's just boring, so let's just convert that into seconds, because it's much more easier, trust me. Okay, so per hour. If you can read this, call me, because I can't read this either. So with that in mind, we're going to convert it to seconds. Now doing this, I forgot the special number you do to divide it by, but let's just do this old-fashioned way, huh? So let's divide it by 60 to get ourselves how many meters per second? Per minute. No, I did the wrong thing. I thought of the wrong thing. Hang on. Okay. Well, it's 60. So, basically, I got in my head when I divided, I got 1333.3 meters per minute. We're getting there. Now, in order to get seconds, we divide again, which I will do in my head again, and I got, well, I already knew I was going to get this, but, because I already did this, but okay. 22.2 repeating meters per second. Now, so yeah, you got 22.2 repeating meters, not like that, let's not write that like that. Meters per second, 22.2 repeating meters per second. Now, let's just mark that on the Adobe Road. We're going to find out the distance between these two cars after one of the cars is doing the 2-second rule. How? Well, if we know that 2.2, if we know that both cars are going 2.2 meters per second, then how many meters per second then how many meters would it be after 2 seconds? Yes, we're going to multiply both. We're going to multiply 2.2 meters per second by 2, so it would be 2.2 meters per 2 seconds. Or, well, you'll get the idea when we put it on there. So it'll just be like times 2, which will equal, you know what, I'm not even going to use my brain power. I might even use a calculator. No, I'm just joking. Is 0.4, sorry. Meters. Okay, now let's put that on the road, shall we? Okay, so now that we have both the final velocity and the initial velocity, what we're looking for is the final velocity of car B. Of car A, sorry, of car A, which is, I'm sorry, I'm confusing this, okay. Of car A. So, in order to do that, we are going to use this equation. Now, we're going to fill in what we know, and then solve for VF. So, VF equals VI, velocity initial, which would be 2.2 meters per second. 2.2 meters per second. That was my mom. I guess I'll add to the credit list. And then, so 2.2 meters per second. That's the velocity, current velocity. Plus, well, actually minus, because the acceleration is going to be negative 6 meters per second, according to someone. Okay, so minus 6 plus negative 6 t. Well, we know what t is. I'm sorry. I realized that I misplaced one of the decimals in my actual work. But anyway, we'll do this together. So it'll be times the reaction time. Okay, so this is the number. We're going to multiply that, and I already multiplied it to save us time, because I don't know why. So that'll give us negative 1.289 10.835 ish. Yeah, that's a long number. You know what? Let's just simplify that to like the nearest 10. That'll be nice. So, congratulations. Negative 1.289108358. You are now being promoted to negative 1.3. Let's give it a round of applause here. Yay. I'm alone in the house, so I'm pretty alone. So that's going to be that. And that's going to be minus 2.2 meters per second equals final velocity. Now, I think you guys can do this on your own, but I'm just going to do it with you just in case. Now, 2.2 minus 1.3 equals 0.9. Yes, that's right, folks. 0.9. That is our final velocity. So, final velocity equals 0.9 meters per second. Now, that's the current velocity of car A while it's after it put its brake on and during car B's reaction time. So let's put that on the graph, shall we? Okay, so now we have the current velocity of the car A during its during the reaction time. Now let's find the distance of car B during their reaction time. So I multiplied, so I have 2.2 meters per second times 0.2, which is the reaction time. And when you do that, you're going to get 0.44. Now, what is that? Well, good thing you asked, because that is the distance that car B traveled during the reaction time. Now, you'll see. Okay, so now that we have that, I'm just going to save that number there. It'll be important later. We're going to use this equation, which is final velocity squared equals initial velocity squared plus 2a delta x. Sorry, just having lunch. Okay, just have lunch. Well, I'm still okay. Now I already put the numbers in there, and so when you square the final velocity, which is 0.9 meters per second, you get 0.81, and initial velocity was 2.2. I think you get it now. And negative 6 times 2 is negative 12. So we already did that. Should have done the other part. Okay, hang on. So next we're gonna try to get delta x by itself, which is simple. I hope. No, it is. Yeah. So we're gonna subtract. Oh my gosh, are there bell peppers in there? Yeah, there are bell peppers in that center. Okay. Okay, so we're gonna subtract negative 4.84 and negative 4. We're gonna do that. Just subtract 4.84 from both sides to try to get delta x by itself. Now, when I did that, I just got what? Yeah, 0.81 minus 4.84. Sorry, negative, so I'm going to get negative 4.03, which equals negative 12 delta x. Now I think you guys know how to do the next part. Divide both sides by negative 12. And you would get a positive number, of course. And what we got was 0.3 or 23335 then 3 repeating, but we'll just simplify it to 0.3. It's like calling someone John Hancock III. Okay, well, 10 first. That example. So we got that equals delta x. Now that's the distance between those two cars. Now, okay, so we're almost done with step 2. So all we need to find out is the distance that both of the cars are going to be from each other. So remember when I tested to see like how far the car B went during the reaction time? Well, here's that number again. We're going to subtract that to the current distance between both cars, and then we'll do something else with that. Why is that flash? Okay, well, anyway, so yeah, so I crunched the numbers again, and I got 3.96 meters. That's because car B moved closer to car A. But you have to also consider that car A also moved, except slower. But at the same time, it moved 0.3 meters. So you're also going to have to add to that plus 0.3 meters, which will get you 4.26 meters. Now, where does that go? Well, I'll show you. Alright, welcome to step 3. Yeah, I got that one right this time. Okay. Step 3. right here is where car A is going to stop, finally. Now, from what we know, we have to find out the time it takes for car... Sorry, I'm still having lunch. For car A to stop from where it's at to 0. So, we're going to use this little equation, which is going to be called final velocity equals initial velocity plus acceleration times time, or TIM for short. No, I'm just joking. So as usual, I always did the math numbers for you. I put them all in there. 0 is the final velocity. 0.9 is the ELAPA. No, not the ELAPA, sorry. The initial velocity. And -6 is the acceleration, as usual. So let's do this, shall we? Negative, so we're going to subtract them both together. You know the deal. Negative 0.9 minus 0.9. And we have negative 0.9 equals negative 6t. T is for time, not for this. I paid food. Okay. Okay. So now we're gonna get t by itself by just dividing. So we divide by negative 6, divide by negative 6, and so that makes us get 0.5. Sorry, not 0.5. Erase that. 0.15 equals the time. So that means that it took 0.15 seconds for that car A to stop. Fascinating. From where it's at, not entirely from 22. You'll get it. You'll get it. Alright, so now we have the amount of time it took for car A to stop. We are going to find the distance that car B took, that car B went through, in the amount of time it took for car A to stop. So we're going to use this equation, which is delta x equals the initial velocity times time plus half of the acceleration times time to the second. Well, time squared. Okay, well, you get that. So, as usual, I did crunch the numbers for you. Delta x is what we're looking for. The initial velocity, which was 2.2 meters per second, times time, which is 0.15 seconds, times plus the acceleration, which is negative 6. And then we have the time again, you know that, so I did all that stuff for you and got negative 0.0675. Great! So now what we have to do is just crunch these two together. Simple. So it's delta x equals 0.33. Well, why am I rewriting that? Good question. Let's just combine these two together, shall we? Okay. So, one minute, please. 1 second. Or, I don't know. I'm just distracting you guys. Minus 0.0675 equals. Okay, bigger number. Not really, but there we go. So, delta x equals 0.2625 t. Now, we need t to be by its... Oh wait, we already have t. My bad. So, there you go. That's the distance that car B went through, which was 0.2625 meters during the car A's breaking point. Made a joke. Okay, well, yeah. Okay, so now that we know the distance of car B during the braking time, let's find out exactly how far car A went while it was braking. Well, until it made a complete stop. So, in order to do that, we are going to use this formula, which is the final velocity square equals initial velocity square plus 2a delta x. Now what we're looking for is delta x. So as usual, I put the numbers already in there. Save time. Really talk. Okay. So final velocity obviously is 0. The initial velocity is 0.9 miles per hour. That's square. And then acceleration -6 times 2 would be -12 delta x. Okay. So first we have to get this by itself. So subtract 0.81 from both sides. 0.81. Okay. So you have -0.81 equals 12 delta x. So squeaky. Why? Okay, next you got it right. You gotta divide both sides by -12. -12. And I did that, and I got 0.0675 equals delta x. Ta-da!
Yay!
That's the distance it took for card A to stop from 0.9 meters per second to 0 meters per second. Okay, now we have the distance between, now that we have the distance between that both cars moved until the car is stopped, we can now figure out the total distance at this current moment. Hang in with me, people. So first we'll subtract the distance that car B moved closer towards the car, which was 0.2625. So we're going to subtract that, and you should get 3.9975. Way too close for comfort already. Just not okay. Well, remember also that during this time, car A moved for the last time a total of 0.0675 meters. So we're gonna add that up, and we are going to get 0.0675, a total of 4.065 meters. That's the distance. Well, now we'll add to Adobe Row. Okay, so now we have the distance that both cars are. Let's find out the current velocity of car B. Now, in order to find that, we're going to have to use this equation, which is the final velocity equals the initial velocity plus acceleration times time. So I already put the numbers in just for you, which is final velocities, which we're looking for. The initial velocity is 2.2 meters per second, and if you multiply the acceleration, which is -6, by time, which is 0.15, you get this. Now I know what to do. So it would be like 2.2 minus 0.09 will give us the final velocity of 2.11, which is meters per second. That's how fast car B is going at the current moment. Reckless idiot. Go. Okay guys, I know you've been with me for 30 minutes, and if you're listening to this, congratulations. I can't believe you've been able to watch this for 30 minutes. Anyway, We're almost done. Two more equations, I promise. We are now in step 4, which is the final step, or stage, or whatever you want to call it. And now we're just going to find out, is there going to be a collision? So, to find that out, we're going to have to find the distance that it takes for car B to go from 2.11 meters per second to 0 meters per second. Now, in order to do that, we're going to have to find the distance, which is delta x. Now, the equation I chose for this, just for you guys, is final velocity squared equals the initial velocity squared plus 2 acceleration plus 2 times acceleration times delta x. So, as usual, I already put the numbers in there. We got 0, which is hopefully the final velocity. And then we got, well, velocity squared, which makes it 0. And then we got the initial velocity, which was squared, which originally is 2.11 meters per second. And then we got that, you know what that is. I hope. I really hope. Because if you don't know what that is, wake up! Wake up, seriously, if you don't know what that is. It's like my third one. I'm really thirsty. It's really hot in here with the computer. Anyway, so, moving on. You gotta get delta x by itself, so what we're gonna do is we're gonna subtract 4.4521 from both sides, negative 4 minus 4.4521. That will give us negative 4.4521. How many times am I gonna have to say? Okay. Equals negative 12 delta x. Now what? Very good! You're right! We're going to divide both of them by negative 12. And that is going to give us point. And now, since I was all nice to you before, at the moment, I don't really give a crap. Let's go with that word. So, right now we got 0.371. Sorry. 0.37. Sorry. I'm so excited. I finished. I'm almost done. 0.3710 8 3 3 3 3 equals delta x. Wasn't that fun? We're almost done, trust me. So yeah, that's the total distance it's going to take for car A to stop. For car B to stop. But is it enough? We will find out that in the next segment, which will be really cool. Right about now. Hello, and now we're going to figure out if those two cars collided. So, we have the total distance of both of the cars. Well, the total distance between both of those cars that are in between each other. And we have the total distance that car B moved until it reached 0. Now, hopefully, if we subtract these numbers, we are not going to get a negative. If we get a negative, that means that they collided. So, here we go. Minus 0.37. I know you guys already know the answer, but I'm just doing this just to annoy you guys. But anyway, 371 0 0 8 3 8 3 3 3 equals. You guys already know this, but I'm just gonna do it just for lulz. So, at the current rate, when both cars are completely stalled, they do not crash into each other, but they are exactly 3.69916667 meters apart. So, in conclusion, they didn't crash into each other. So that's a good thing. Well, so in conclusion, I can conclude that the 2-second rule actually does work. So pretty impressive. You can do with math. Well, that's pretty much it. I think I've wasted enough of your time. And bye. Yeah, seems good. Bye. 3, 2, 1, play.